Once regarded as a distant and mysterious member of our local planetary system, Pluto has long fascinated astronomers. Though it was reclassified from a full-fledged planet to a dwarf planet, recent surprising remarks by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the limelight. They suggest that this icy celestial body might one day be on a collision course with Neptune. How could such an event be possible? And what would the consequences of such a cosmic catastrophe be? Is this simply a fascinating anomaly in our solar system, or does it hint at a greater impending disaster? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto's story is unlike any other. Since its discovery in 1930, it has never completed a full orbit around the Sun, taking a staggering 248 years to do so. Its orbit is highly elliptical and significantly tilted, about 17 degrees relative to the ecliptic plane, making its path strikingly different from the nearly circular orbits of the major planets. This unusual orbit intersects closely with Neptune's, raising concern among scientists, including Tyson and Kaku, about the possibility of collision with potentially serious effects for Earth. Despite this apparent risk, Pluto has never collided with Neptune. This paradox is explained by the complex gravitational interplay between Pluto, Neptune, and the Sun, a classic example of the three-body problem in celestial mechanics. This problem involves predicting how three gravitationally interacting bodies influence each other's motions, a notoriously difficult puzzle in astrophysics. Several factors contribute to Pluto's orbital stability. Asynchronous libration means that whenever Pluto crosses Neptune's orbit, it is always at least 90 degrees away from Neptune itself, maintaining a safe distance. Orbital precession causes Pluto's orbit to tilt upward at key points, ensuring it passes above Neptune's path. Additionally, the VZK oscillation describes the mutual gravitational influence between Pluto, Neptune, and the Sun, which further stabilizes Pluto's trajectory and prevents chaotic shifts that could lead to collision. These intricate dynamics reveal that even seemingly erratic orbits follow hidden patterns and laws. Though Pluto's orbit may appear unpredictable, these gravitational safeguards have kept it on a stable course for centuries. However, mathematical simulations from the 1980s indicate that despite these stabilizing effects, Pluto's orbit remains somewhat unpredictable, and even minor changes could alter its path over time. By studying these phenomena, scientists gain valuable insights not only about Pluto and our solar system, but also about the broader mechanics governing planetary and stellar systems throughout the universe. Initial conditions can cause major changes over thousands of years. However, Pluto's orbit has been shown to remain stable over extremely long periods. Further research has revealed how Neptune, Jupiter, and Saturn influence Pluto's trajectory. Notably, Pluto and Neptune share a unique orbital resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship plays a key role in maintaining Pluto's orbital stability. Jupiter's powerful gravity also contributes significantly by preventing Pluto from drifting too close to Neptune's path. Saturn's gravitational pull adds yet another layer of stability. Together, these giant planets work in harmony to ensure Pluto moves safely through space without major disruptions. Without these gravitational interactions, the solar system could be far more chaotic, with objects like Pluto potentially colliding with planets or being ejected from their orbits, causing a chain reaction of events. Understanding Pluto's orbit is particularly important, especially amid discussions about a possible future collision with Neptune. This understanding also sheds light on the dynamic nature of our nearby planetary system. Pluto's case illustrates how even seemingly unstable orbits can achieve equilibrium through the complex interplay of gravity and orbital mechanics. It also highlights the importance of ongoing observation and study to deepen our knowledge of the universe. Studying celestial bodies often reveals their unusual behaviors, and Pluto's orbit is a prime example. The concept of orbital chaos, where a body's orbit is highly sensitive to initial conditions, is clearly seen in Pluto's path. Even slight changes in Pluto's position or velocity can cause significant shifts in its long-term orbit. Automated simulations have been crucial in helping scientists model these gravitational interactions between Pluto, Neptune, and other solar system bodies. By adjusting small variables in these simulations, researchers observe how tiny differences can drastically change Pluto's trajectory. In the late 1980s, such simulations offered fascinating insights into Pluto's orbit. Although stabilizing factors like asynchronous vibrations and orbital precession help maintain order, Pluto's orbit can still behave unpredictably if its initial conditions shift slightly. Despite this apparent chaos, Pluto's orbit remains stable over billions of years, suggesting an underlying order governs its journey around the Sun. Predicting the movements of celestial bodies with irregular orbits like Pluto is a tremendous challenge. The inherent unpredictability of these systems means long-term forecasts come with considerable uncertainty. While mathematical models are invaluable for understanding and anticipating celestial motion, they also expose the limits of our predictive power, as even tiny errors in initial data can lead to drastically different outcomes. The chaotic nature of orbits like Pluto's serves as a reminder of the universe's ever-changing dynamics. Though we made remarkable progress in space science, Pluto's case underscores how much remains to be discovered. The gravitational influences of the giant planets on Pluto offer important insights into how the entire solar system functions, showing how each planet's position profoundly affects the stability and paths of others. So why have some prominent astrophysicists recently expressed concerns about a possible collision between Pluto and Neptune despite destabilizing forces? Neil deGrasse Tyson, a leading astrophysicist and key figure in Pluto's reclassification as a dwarf planet, provides a unique perspective on the mysteries of our solar system, especially regarding Pluto. Tyson's insights reflect the evolving understanding of celestial mechanics and a renewed public interest in often overlooked cosmic phenomena. Astrophysicist Neil deGrasse Tyson views the reclassification of Pluto not as a demotion, but as a necessary update reflecting our growing understanding of the diverse objects orbiting the Sun. He believes that the complex nature of orbits like Pluto's highlights how much remains to be discovered in space. This ongoing curiosity drives the excitement of space exploration. Despite Tyson's optimism, his concerns about a possible collision between Pluto and Neptune indicate that many aspects of Pluto's orbit are still uncertain. Will Pluto actually collide with Neptune, or is this just another example of the confusion inherent in the ever-evolving cosmos? Only time and further study will provide answers. For now, we are left with a heightened curiosity about how little we truly know about our solar system. We continue to investigate these celestial phenomena in hopes of uncovering the universe's hidden secrets. The possibility of a Pluto-Neptune collision raises more questions about the mysterious and intriguing universe we inhabit. Such a scenario challenges our traditional ideas about planetary stability, especially considering the current dynamics of their orbits. Pluto, located on the outer edges of the solar system, is far from the major planets, while Neptune, a massive gas giant, exerts a powerful gravitational influence. An impact between these two would have significant consequences for our understanding of gravitational interactions and the solar system's evolution. To grasp the dynamics of a potential collision, it is important to consider the compositions and characteristics of Pluto and Neptune. Pluto, though classified as a dwarf planet, is made of various frozen substances due to the extreme cold in the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere mainly consists of nitrogen, methane, and carbon monoxide. In contrast, Neptune is a huge gas planet primarily composed of hydrogen, helium, and other lighter elements, with a dense and deep atmosphere. A collision between these very different bodies would drastically change their structures and behaviors, possibly creating an event observable from great distances. What makes this hypothetical collision particularly interesting is the influence of other planets in the solar system. While Neptune's gravity helps stabilize Pluto's orbit, it is not the only factor. Jupiter, with an immense mass and strong gravitational pull, also plays a stabilizing role by preventing Pluto from drifting too close to Neptune. Saturn's gravitational effects further complicate the outer solar system's dynamics, making a catastrophic collision between Pluto and Neptune highly unlikely. Despite these risks, ongoing research shows that the relationship between Pluto and Neptune is more intricate than a simple collision course. The gravitational resonance between the two, where Pluto completes 2 orbits around the Sun for every 3 orbits by Neptune, creates a cosmic lock that prevents direct collision. This resonance is key to maintaining the stability of their intersecting orbits, ensuring that Pluto and Neptune, despite crossing paths in space, have never collided